So in a reverse bias PN junction, we effectively have the exact same thing as a forward bias PN junction, but the polarity of our applied voltage has been switched. So it would look something like this. Down here is going to be our applied voltage. And now the negative polarity of our terminal is going to be connected to the P side of our junction, and the positive polarity terminal of our battery is going to be connected to the N side of the junction. Let's talk about what impacts that's going to have on the junction as a whole, and then we'll look at carrier concentrations and all of that kind of good stuff. Okay. So how does the polarity, or how does the direction of the external electric field compare to the direction of the internal field of our junction in this case? They're both in the same direction. So that means they're going to add together, right? So what is the consequence of those two fields adding together going to mean? The barrier is increased, and we have a very strong field pushing majority carriers away from the edge of the depletion region, right? It should hopefully be obvious that the width of the depletion region is also going to be larger in the case of a reverse bias junction, because we saw it get smaller in the case of a forward bias junction. So if this is the edge of the P side, so this would be negative WP, and let's say that this is the edge of the N side. Let's take a quick look at what our carrier concentrations should look like. So starting with holes on the P side of the crystal, we should have something like this. So it's going to be at some constant level until we get into the region of the junction, and then it's going to fall off very, very steeply. And we're going to see something similar to that for holes on the opposite side of the crystal. And then if we look, let me write some things down here. So this is the hole concentration on the P side of the crystal at thermal equilibrium. This is the hole concentration on the N side of the crystal at thermal equilibrium. For electrons, we're going to have something like this, where this is the electron concentration on the N side at thermal equilibrium. And this is the electron concentration on the P side at thermal equilibrium. Excuse me, thermal equilibrium. So our electric field total is going to be in this direction, and just for the sake of argument here, we have bound negative charge and bound positive charge, and this is E total. So why do the majority carrier concentrations suddenly fall way down when we get to the edge of the depletion region? Exactly right. North nailed it. We have a very, very large field that's pushing majority carriers away, right? So holes act in the same direction as the applied field. So holes are going to get over here and they're going to get pushed back, right? Electrons act in the opposite direction of the field. So they're going to get over here and they're going to get pushed this way. What's going on with the minority carriers? What was that? You're just getting stuck. Yeah, that's pretty much it. Exactly right. So in a forward bias PN junction, we had a process called minority carrier injection, where minority carriers were being injected into the opposite side of the crystal. Here we have what's called minority carrier extraction. The electric field strength is so large that any minority carriers that get over to this side of the junction get swept through to the opposite side of the junction. So we have a very, very similar case to what we had for forward bias junctions, but now instead of having majority carriers move across the crystal, we're having minority carriers move across the crystal. And it's still a diffusion related process because we see that we have a gradient here, right? So there are some number of electrons here. There are effectively no electrons here. So electrons are going to diffuse from left to right, get swept through. Holes are going to diffuse from right to left and get swept through. I'm going to write down those diffusion directions here just to be consistent. So here we have electron diffusion. Over here, we have, it's not how I've been doing it. Like so, and then those carriers get swept through, right? So those carriers getting swept through are going to cause a current to flow, right? We have carriers moving across the crystal, electrons are moving from left to right, holes are moving from right to left. What direction should our current be flowing? From right to left. So in the opposite direction, we saw for a forward bias crystal, right? So for a forward bias crystal, we saw a net current flowing from left to right through the device. For a reverse bias PN junction, we see a net current flowing from right to left. How do we think the magnitude of this current in a reverse bias situation is going to differ than the magnitude of a current in a forward bias situation? Much, much less, right? Because in a forward bias crystal, we have majority carriers being moved across our space charge layer. And we can see from our graph here that there are way more majority carriers available than there are minority carriers. So when the current is dependent on the diffusion of majority carriers, we see very large currents. And by large currents, I mean on the order of milliamps, right? When we have minority carriers that are responsible for our current, we wind up seeing very, very small currents on the order of nanoamps, picoamps, and all of that kind of good stuff. Mathematically, it's literally the exact same situation that we had previously. In fact, we're going to use the exact same equation because it's fundamentally the exact same process. We're just now looking at what's going on with the minority carriers. So our current density relationship, JD total, is literally going to be the exact same equation. So we're going to have, let me move this out here, Q times Ni squared dP divided by LP ND plus dN divided by ln NA, all multiplied by the exponential function of negative Q VR. So VR is our reverse bias applied voltage divided by KBT minus 1. So one thing that I do want to point out here is that we are assuming that VR is a positive quantity. So when we looked at the total diffusion current density for a forward bias PN junction, it was literally this exact same equation, except that we didn't have a negative sign right there. Okay. So realistically, we could not worry about VF for forward bias and VR at all for reverse bias and just call it V bias, where we're always assuming our battery voltage is applied in a forward bias configuration. And whenever we have a reverse bias, we could just say, well, it's a negative voltage and use the exact same equation for everything, which is really what I'm going to do from here on out because I don't want to remember the damn difference. Okay. Well, let's talk about what's going on here, right? So when we had our forward bias PN junction, we saw that for an applied voltage that was just a few thermal voltages, our current got very, very large, and it was going to exponentially grow to where this factor of -1 really didn't mean anything. Now let's consider what happens when VR gets large, like more than a few thermal voltages. What's going to happen to this exponential function? It's going to go basically to 0, right? So e to the some negative large number is going to get closer and closer to 0 the larger that number gets. And so we're going to have our current dominated by this -1 term. Okay. So we're going to see a current flowing in the opposite direction. It's going to have a fixed value. And the fixed value is that saturation current density. This guy right here. JS. The exact same JS that we had in our last class meeting. Okay. So we've described current flow, really doing no analysis whatsoever, just understanding that the same mechanism is happening here that we saw in our forward bias current. What do you think is going to happen to our equation for the width of our depletion region? Yeah. So previously it was like V naught minus VF. Now it's going to be V naught plus VR. Exact same relationship, right? So 2 epsilon over Q NA plus ND over NA times ND times V naught plus VR. And again, we could literally just use a single relationship using a bias voltage that is assumed to be forward bias and letting reverse bias just mean a negative applied voltage and come up with the exact same result. Let's see, we've talked about that. We've talked about that. I don't want to talk about that because it doesn't make a whole hell of a lot of sense. Let's talk about depletion layer capacitance. Okay. So we know that for a forward bias junction, we had a capacitance that was associated with the injected minority carriers on either side of the junction. We don't have anything like that here. So we really just have our unbiased junction capacitance that's going to change slightly because when we apply a reverse bias voltage, the width of our depletion region changes. So we still have a voltage controlled capacitance, but it's a little bit easier to understand because it's literally just a scaled version of the junction capacitance. So without going into a ton of the math, it literally just comes out as follows. Our reverse bias junction capacitance is going to be our unbiased junction capacitance divided by this quantity. 1 plus our reverse bias voltage divided by our built-in voltage to the mth power, where m is what's known as a grading coefficient. And it is equal to 1/2 for what are called step junctions, which is what we've been dealing with. So where our carrier concentrations have an abrupt shift and it's going to be 1/3 for linearly graded junctions. Meaning that our carrier concentrations change linearly across the crystal. So really, this is just telling us that depending on how our PN junction is formed, we are going to have a square root relationship here or a cube root, oh, goodness gracious, cube root relationship down here. Okay. For the intents and purposes of this class, we'll practically always just say that m is equal to 1/2 for ease's sake. But I just wanted to let you guys know that there is technically a different thing. So this reverse bias junction capacitance is usually used in the application of varactor diodes, what they're called. So if we look at this thing, how does our capacitance change as our reverse bias voltage gets larger and larger and larger? What's happening to our junction capacitance? It's getting smaller and smaller and smaller. Mathematically, this makes sense. Hopefully, intuitively, it makes sense as well, because the edges of our space charge region are getting further and further apart. So effectively, the gap separating our plates is getting larger, and we know that the capacitance is inversely proportional to the distance between the plates in a parallel plate capacitor. So everything's going exactly how we should expect. All right. Let's talk very briefly about the energy band structure of a reversed bias junction so that we can talk about the two different breakdown mechanisms, and then we'll be done. All right, so I'm going to draw kind of an approximation type thing for the crystal up here. So this is the P side of our crystal, and then this dashed line is representing the width of the depletion region into the P side. Here's our metallurgical junction. And then over here is the width of the N side of the depletion region. And then this is the neutral N-type region of space, right? If we look at our energy bands, we're going to have something like this. So our energy band for the conduction band on the P side of the junction is going to be flat until we hit our space charge layer. We're going to have band bending in our space charge layer because we need the Fermi levels to be equal on both sides of our junction. So we'll deal with that here in a moment. Down here, I'm going to put the P side of the valence band. And we know that on the P side, we just have lots and lots of holes available, right? So I'm just going to draw a whole bunch of holes down here saying that these states are largely filled with holes. Our Fermi level on the P side should be somewhere down here. Now over here on the right-hand side, I'm going to draw the conduction band for the N side of the crystal. So this will be ECN. Here will be EVN. And somewhere around here will be the Fermi level for the N side of the crystal. And then, like I said earlier, we're only going to see that the bands bend in the region of the space charge layer. So up here, sorry, let me define just, we have a whole bunch of electrons because it's the N side of the crystal. You're going to see something like this. This distance right here is just Q times our reverse bias voltage. So that's going to be the difference in the Fermi levels. So when we have our Fermi levels would have to be equal to each other if we had a junction at thermal equilibrium with no external excitation or anything like that. So we would see some sort of band bending, but effectively our reverse bias voltage is going to cause the N side of the crystal to shift down at a lower potential. And it's going to cause those Fermi levels to slightly separate depending on how much reverse bias voltage that we apply. So we have a few minority carrier holes over here, and they see let me do this in a different color because this is getting too damn busy. So this level right here is supposed to represent the energy of the valence band on the P side, but I drew my Fermi levels effectively lining up there. So I need to give myself just a little bit of separation so that I can help define something here. So what I'm trying to quantify here is this total barrier potential. V naught plus VR. And then we're going to see something pretty similar over on this side as well. So if this guy represented ECN, this would be our barrier potential on this side. So it's going to be very, very hard for our electrons over here to climb this slope because the potential is very large. But it's going to be pretty damn easy for minority carrier electrons here to roll down this slope and get to this region, right? So that's what our minority carrier extraction process is going to look like. Electrons going down have a very, very easy time of it, and holes going up have a very, very easy time of it. So that we can see that minority carriers are principally responsible for current conduction in a reverse bias junction. All right, so mathematically we saw, let me scroll up here just so we can see it. It looks like the current flowing through our junction, once we're beyond a certain point, is effectively independent of our applied voltage, right? So if I were to plot the characteristic curve for a PN junction, where this is current on this axis and voltage on this axis, we should have something that looks like this for forward bias. I just want to note, this is typically on milliamp scale. And then something that looks like this for reverse bias, where this is typically, let's say, nanoamps to picoamperes. Incredibly small. So that once we're a few thermal voltages reverse bias, our current is pretty much flat. But this won't always be true. Okay? If we put enough of a reverse bias voltage across our device, we are going to experience breakdown. All right. So we should see that at some voltage VBR, our current falls off extremely abruptly. There are two principal mechanisms for reverse bias breakdown that we are going to see. The first that we're going to talk about is what's called avalanche breakdown. So avalanche breakdown is breakdown that is unintended. So in avalanche breakdown, let me write this out. So we need to have a lightly doped PN junction. So let's talk about why that is by looking at this energy band diagram here really quick. What do we know about doping concentration levels and the width of the depletion region? The more doped, the smaller the depletion region is, isn't it? I. Yeah. It can be a J as well, it doesn't really matter. Because J is just I times the, or excuse me, I is just J times the cross-sectional area. So whatever floats your boat, it's going to behave the exact same way. So if we have a lightly doped depletion region, or excuse me, a lightly doped PN junction, that means that the width of the depletion region is going to be very large. The reason why the width of the depletion region being very large is important is because there's a phenomenon called tunneling. Have you guys heard about tunneling before? Right. So what is tunneling, the probability of tunneling most directly related to? Distance. Okay. So it's going to be very hard for charge carriers to tunnel from the left side of the junction to the right side of the junction or vice versa if the depletion region is very, very large. Okay. So no tunneling is going to occur. Instead, we have a very, very wide region of space, so that an electron that is diffusing from the P side of the depletion region will be imparted with an extremely large electric field. Okay, so something like this. Here's our crystal. We're putting a hell of a reverse bias on it. So the width of the depletion region is going to be pretty damn huge. So this is our neutral P side. Over here is our neutral N side. Everything in between is our space charge region. Let's put our voltage down here. Negative, positive, VR. And we can see that our combined electric field is very, very large. Okay. So let's say that we have an electron. Here, minority charge carrier for the P side of the junction. it's going to diffuse towards the edge of the depletion region, and then it's going to see this really, really, really big field. Okay. What's the energy of an electron under an applied voltage? UV, right? So if we have a really large field, it's effectively going to be imparted with a whole hell of a lot of energy. And so this electron is going to be shot forward until it hits the nucleus of one of those bound dopant atoms. And then we're going to see almost like an explosion where it gets to knock a subsequent electron out. But that's also going to create a hole. And these electrons that get knocked out can further collide, causing more and more electrons to shoot out and subsequent collisions to take place. Now I'm going to throw some holes in here just for shits and giggles. So avalanche breakdown is a very, very bad thing, in as much as we are giving our minority carrier electrons over from the neutral regions enough energy to literally break the valence bonds that are holding our crystal together, right? We're breaking those electrons off, and that's what's causing conduction to flow. So avalanche breakdown is causing irreparable damage to our crystal. So we need to avoid that if at all possible. So that's why if you put too much current through one of these things, it's literally going to burn out. Okay? Now, the other mechanism is called Zener breakdown. So for Zener breakdown, we need a very heavily doped junction. We need a very heavily doped junction because we want tunneling to occur, because tunneling is a way to allow for a safe amount of current to flow through our device. We're not going to break any of the bonds or anything like that. So effectively, for Zener breakdown, we're going to have a situation that looks something like this from an energy band diagram perspective. Where, like I said before, only where the bands bend are we in our depletion region. So our depletion region is very, very small. And we should be able to see that electrons in the valence band of the p side of the crystal see almost an equal potential surface over here on the conduction band of the inside of the crystal. And since it's just a short distance, they can pretty much just hop on over freely. So we get large amounts of current flow during Zener breakdown, but we're not causing the physical damage that avalanche breakdown causes. We'll talk more about Zener breakdown when we talk about Zener diodes and all of that kind of stuff in a couple of days. All right, I'm done. Have a good rest of your Friday.